Okay, great. We are recording now. Okay. Alright, so today we are going to do the forces tutorial. Okay, and the first topic that we are going to encounter in forces is Hooke's law, okay, and elastic potential energy. So basically in Hooke's law, right, our most important equation, of course, okay, which you can solve all Hooke's law equation is F equals to Kx. Okay, that is what we want. F equals to Kx. Okay, so basically no matter how complicated a system of springs may be, or if it's just one spring, F equals Kx will hold for each individual spring in the system. Okay, so for question 1, right, we have 3 springs, okay, they're negligible mass, they extend a certain amount by x, okay, when a weight W pulls on all of them. Okay, so let's go straight to the question. Okay, now, very important thing for Hooke's law is that when we see a system of springs, right, we are able to identify how much force acts on each individual spring, okay, when we just want to consider one spring out of the entire system. So we have 3 springs in parallel in this case, and the total force that acts on the system is W. Okay, now if W acts on 3 springs in parallel, each spring then must experience W over 3. So applying our Hooke's law, okay, F equals to Kx. Okay, when this system is experiencing a force of W, each spring's extension is x in this case. Alright, so W over 3 equals to K, which is a spring constant of one spring. Okay, is a spring constant of K times x. So for a spring, right, regardless of what system it is in, okay, its spring constant will always be the same. That's whatever holds constant. So let's make x the subject. We find that K is W over 3x. So that's the spring constant for any one spring in this system. Now we're going to be mean people, and we're going to actually remove one spring to make the load on the rest of the springs harder. Okay, we're going to remove one spring, so here, it's gone. Ta-da! And then after that, we increase the force or the weight that the system experiences by 2 times. So now there's 2W over force acting on the entire system. So now, right, each spring experiences a force of W, okay, and the extension changes definitely, but we're not very sure what it is. The extension changes to Y. Okay, but because Hooke's law still holds, we can write an equation down for this particular spring. W equals to K times Y. Okay, from this. W equals to K times Y. But we know K, right? K is the same regardless of what system the spring is in. And we know K is W over 3x from the earlier example. So W over 3x, we do a substitution, equals to like that. Okay, and we notice that there is a W on both sides, so they get to cancel each other out. Okay, then we can get Y in terms of x. This will say Y equals to 3x. And that's our solution for question 1. Any problems? Yeah, Javier, what's the question? Do you have a mic? Do you want to talk? Okay, then you can just type it out. If the spring constants are different, will the weight still be equally distributed? Okay, let me start. Okay, so this question is okay, right? So let's have a discussion about what if we have more springs, okay? So this one I'll just rename. Okay, looks like I can't rename without my keyboard. Okay, doesn't matter. If the spring constants are different, will the weight still be equally distributed? Okay, let's take an example, okay, where I have two springs. This one is spring constant K1 and this one is spring constant K2. Okay, and the weight is W. So intuitively, right, some of you may think, oh, because there's two springs, even though they have different spring constants, maybe the force is still equally distributed to the two of them. Now, what we know is true is, for all cases, is that F equals to Kx for an individual spring. Okay, and when I put two springs parallel like this, okay, one thing must be sure for these two springs. They must both extend by the same amount. Otherwise, you'll get some very singy case that it looks very weird. Okay, it will look something like this. Okay, but we know that doesn't happen in real life. So they must extend by the same amount. If they must extend by the same amount, we can say that we can say that they extend both by an amount x. So if I were to write down F equals to Kx for each individual case, okay, for K1, okay, whatever force that's acting on it, F1 will be equal to K1 times x. And for F2, it will be K2 times x. And the total F1 plus F2 must be equal to W. Now, F1 and F2 are different, right? Because K1 and K2 are different. So if K1 and K2 are different, then F1 and F2 can't be the same, right? One of them will be larger and one of them will be smaller if K1 is not equal to K2, because they must both add up to W. So the only case where the force on each spring will be the same is exactly when K1 equals to K2. Okay, like our this example in question 1. So for parallel system, right, if the springs are uneven in terms of their, what's this called, spring constant, then the forces are not uniformly distributed. But what we do know is that they both extend by an amount x on both sides. Okay, that is all. Does that answer your question, Javier? Okay, great. Okay, that's question 1. Any more questions for question 1? If you have, you can just type it there. If not, I can just proceed to question 2. Okay, question 1 was pretty interesting. Okay, question 2 is a bit more challenging. Okay, question 2 looks like this. A wire W of length L is fixed at one end and pulled by a force F at the other end. The wire extends by X. So the important information here is this. Oops, okay, that's quite disgusting. Let me use a nicer highlighter color. The wire extends by X when the force is F. Okay, so it means that for this type of wire, right, regardless of what kind of system is going to be placed in, how complicated the system is, okay, whenever a force F acts on it, it will extend by X. That's all. Okay, which means that we can find its spring constant K equals to F over X for this type of wire, for just one. Okay, now in this example, right, they want to put 3 wires, okay, in a very complicated scenario like this. Okay, one of them is in series with 2 and the other 2 are in parallel. Okay, so it looks like this: one in series and one in parallel. Okay, now let's take a look here. Okay, for just one wire, right, we know K equals to F over X. Okay, now I'm going to split the complicated case, right, okay, into different segments, and I'm going to label all of them properly. So this is going to be our example in the question. Let me just check, is the force F? Force is F. Okay, now I'm going to call this one A, B, C. Okay, now the force on B and C is definitely F. Agree? Because for this case, B and C, the force here is F. Which means that the force on B or C is F over 2. So for B and C, the force is F over 2. For A, however, the force is just F. Okay. Now, let's find the extension of each of these springs. Okay, the question wants us to determine the total extension of the composite wire, which means we need to know the extension of each of the wires if we are to find the total extension. So, for the first spring A, okay, let's write down the equation. F equals to KXA. But we know that F equals to KX for this wire. Okay, F equals to KX. Okay, so this means XA is just X. KX. So XA is just X over X. Okay, that's XA. XB and XC equals to, since the force is divided by 2, it is F over 2K. Alright, so we can transfer this information back to our diagram. Okay, A extends by X and B and C extend by X over 2. So we know how much each of them extends. So the total extension is just given by XA plus XB. So it's X plus X over 2. Okay, or we can use the expression that we have already found. Okay, XA is X, right? So it's Fx. No, there's bird outside. Plus F. Sorry, not Fx. Let me see. I made an error here. This one is not Fx. This is F over K. F over K plus F over 2K. So it depends on what you want to leave your answer in. Okay. For this question, I never specify whether you're supposed to leave your answer in terms of X, okay, or do in F and K. Either is fine. Okay, so let's just leave our answer in F and K. So it's 3 over 2 F over K. Okay, and that will be the answer. Any questions? Wow, really hot. Yeah, okay, can have a toilet break, and now I explain why spring A and the combination of spring B and C experiences the same force. Okay. Yeah. 1.5 X, yeah, that's okay. Sorry, you were supposed to leave it as 1.5x or... Okay, what we're supposed to leave it as decimals. Or X is fine. Either is fine. Okay, now, a question asks, how come, right, okay? How come I know that the spring that is in series, right, also experiences the force F? Okay, let's consider a very simple example. Okay, now let's say I have two springs, spring A and spring B. Okay, and the force F pulls on spring B. Okay, if I look at the forces that act on spring B, okay, it is F, right? But on the other side, right, spring A will pull on spring B with a tension. So this is spring B. Okay? So spring A pulls on spring B with a tension. We call this tension TA. Now, for spring A, it will look like this. There'll be a tensional force from the first spring, spring B, as well as a force that the wall acts. Okay, I'll call this force Fw. Okay, now, will you agree with me, right, that the tension forces must be equal because they are opposite and they are equal and opposite reaction forces? TA must be equals to TB. Okay, so if TA equals to TB, and the spring B doesn't accelerate to the left nor to the right, if spring B doesn't accelerate to the left or to the right, then T must be equal to F. If T must be equal to F, then TB must be equal to F. So spring A also experiences force F. Okay? Spring A also experiences force F. So spring B and spring A both experiences the same force. The force that's pulling on both springs will act on both springs as well. That's all. Did that answer the question? Okay. Good. If that's alright, we can proceed with part B. Let's see the question what they want for part B. Part B, they want us to determine the EPE stored in the composite wire in terms of F and X. So in terms of F and X, we choose this one. E equals to half Fx. So E total must be equal to E stored in spring A plus E stored in spring B plus E stored in spring C. But B and C, we know they are the same, right? Because they are identical. Then it's just spring A plus 2 times E spring B. Okay? Now, we use half Fx. So for spring A, half at a force Fx on spring A, and spring A, we know the extension is X. For spring B, we know the force acting on it is F over 2. Okay? And we know that, oh sorry, I forgot the half. Let me put the half in first so that it's nicer. Half. We know that the force acting on spring B is F over 2. That is from 2A. Here, we see that the force acting on it is F over 2. Right? And then the extension of spring B is also half of that of X. Okay. We know the extension is half of that of spring A. So it's X over 2. Then we can add it together. This 2 cancels this 2. So we have half Fx plus quarter Fx. This gives us 3 over 4 Fx. Which is the total energy stored in the entire system. So basically we just analyze how much each spring has, how much energy each spring has, and then we tally it up to get the total energy stored. Okay. Yes, this is what you mean, right? If I take the total energy, okay, is equal to the half of the total force times the total extension, you will get the same thing. half, total force is F, okay, total extension is 3 over 2 times X, and you get back 3/4 Fx. Good. You get the same result. Okay. So in this case, we're analyzing each spring energy and in this case, we are taking it as one system. And you'll get the same result because they are compatible. Okay, alright. Part C. Let's see what the question wants. Part C. The force acting on each wire, on the entire wire system is now tripled. Okay? So F, I will change it to 3F. Okay? Find the change in EPE stored in the composite wire. Change in EPE in the composite wire. Okay? Now, we know that for one spring, right, when the force is tripled, the extension is tripled. So if we take our expression from part B, okay, which is E total, oops, let me use black. E total is given by 3 over 4 Fx. 3 over 4 Fx. If I replace F by 3F, and I replace the extension by x prime, which is 3x as well, I will get 9. Oh wait, sorry, a much bigger number than that. 6.75 Fx. Okay, which is 27 over 4 is 6.75. Okay, that is the final state that it is in. Okay, or on the other hand, okay, if I use the result from question 2a, okay, where the total displacement, okay, is 1.5x, okay, and I plot it on a graph like this, okay, our 1.5x occurs when the force F acts on the system. When the force is increased to 3F, the extension will increase from 3 over 2x to 9 over 2x, which is basically 3 times. Okay, now the question wants change in energy. So we have to give it change in energy. Which is E final minus E initial. And E initial was the energy from part B, 3 over 4 Fx. Here we have 27 over 4 Fx. So the final answer is 6 Fx. Okay, we get 6 Fx. Now, looking at the graph, how is it done then? Okay, basically what I can do is I can take the area of this big triangle, which is half times 3F times 9 over 2x, minus the area of this small triangle. That will give me my shaded area, which is the change in EPE stored inside this spring. Is it clear to y'all? Any questions? Any questions? Okay, basically, I guess the lesson learned here is that, okay, when the force triples, right? Okay, when the force triples, the extension for each spring triples as well lah. Okay, so I can either take the results of B or A to use in my working, or in fact I can even just scratch a graph and then find the answer this way as well. Okay, both ways are fine, and both ways we can get the total energy change as well. But the most important thing, I suppose, which is a mistake that some of y'all made during the class test, is this: change in energy is always final minus initial. Okay, so if you need to memorize something, that's what you need to memorize. Change in energy is always final minus initial. Okay. Now, let's take a look at question 3. Question 3 in the forces tutorial says that an ice cube of site H is dropped into pure water of density 1000 kg per meter cube. When it reaches equilibrium, the ice cube sticks a particular amount above the water level, 0.0833 H. Assuming that none of the ice has melted, find the density of the ice. Okay, so looking at question 3, okay, I've drawn a diagram down already. Okay, the sides are all H. Okay, so clearly the base area A is H square. Okay. Now, we know that this ice cube, okay, floats. So according to principle of flotation, for any object, that's floating, okay, the two forces that act on it, the weight and the upthrust, must balance so that the object remains in equilibrium. Otherwise, the object will start sinking some more or floating some more. So for this ice cube that is floating, we know that upthrust must be equal to its own weight. Right? So from there, we can work using these nice equations. Upthrust is nothing but the weight of the fluid displaced, which is basically the volume of the ice times the density of the ice times G. And the weight of the water is the volume of the ice cube, the weight of, equal to the weight of the object. It is equal to the, oops, I'm sorry, I mislabeled this part. Okay. The weight of the object is the volume of the ice times the density of the ice times G. Whereas the upthrust, right, is equal to the amount of fluid displaced, which is this amount here, which is the volume of the water displaced times the density of the water displaced. Okay, I say one more time. The ice is partially submerged, so it has a submerged volume of this shaded region here. That amount of volume has displaced water, and that amount of water that is displaced, its weight is equivalent to the upthrust that's experienced by this object. So upthrust is equal to the volume of the displaced water, which looks like this: density of water, volume of water times G. And the weight of the ice itself is volume of the ice, density of ice times G. Okay, now we know the volume of the water, right, is just H cube, because the sides of the cube is H. The volume of the ice, is H cube. And the density of the ice is rho ice, and that's what we need. And G is here. Okay, on the left hand side, we know density of water, we know G, and the volume of the water is given by this place is given by the shaded region, which is base area times 1 minus 0.00833. So it is 1 minus 0.0833 times H squared, which is our base area. So let's cancel what we can cancel now. Okay, H cubes cancel, G's cancel, so we're left with this one rho I, the density of ice that we want. Okay, let's make it a subject. Density of ice equals to 1 minus times density of water is given to be 1000. So this gives us approximately 917 kg per meter cube. Yeah, that is given. Okay, so density of water is about 1000. Compare that with the density of ice, which is 917. Okay, percentage density of ice compared to water is about 92%. So ice is slightly less dense than water. Okay. If we were to have a ship in water, okay, and it encounters an iceberg, oops, okay, let's say a spherical iceberg, okay, the ship will collide with the iceberg even before the top of the ship sees the iceberg. Okay, that's because most of the iceberg is actually submerged. And if you know, this is the story behind the Titanic. Okay, they collided with ice, even though the top part of the boat doesn't collide with the iceberg. The bottom part would collide first because most of the iceberg is actually submerged. Okay, so in GP, right, you may use the word tip of the iceberg. Okay, now you know how to derive the tip of the iceberg. Okay, so that's question 3. Any questions? Yes, Hilda? No, I just want to calculate the percentage density of ice compared to water, just for your information. The question actually ends here already, sorry. The question ends here, okay? The rest is just to discuss what this means to us. I mean, just a number, 917 kg per meter cube. Nothing very important, okay? But it also tells us that, okay, because the density of ice is only slightly less than water, so when it floats, right, only a very small part of it is above the surface. Zachary, I'm talking about iceberg. Okay, sorry. Let me include the iceberg. Okay. Yes, the sing. You got mic? H rho G is what? Pressure, right? No, do you have mic? If you have, I can enable it. Okay, you can use H rho G Okay, I suppose you'll be using pressure then. Okay, but it's definitely doable as well. Do you manage to get a solution with it, which gives you the same answer? Wrong ah. Okay, maybe you can show me in school lah. It's more convenient than doing it here. And I only got limited time to use it, that's why. Okay. Yeah. Okay, that's that. Okay, we have time after the lesson, right? I will give you a joke. Okay. That's question 3. Okay, we're going to stop at question 4 today. Okay, I think question 4 is the hardest question. Okay, a person rows a rowboat in a small pond and throws an anchor overboard. Describe and explain what happens to the water level of the pond. Okay, basically, here we're supposed to derive what happens to the water level of the pond. And I guess when students read this question, right, the common misunderstanding is that, I just say whether it rise or it don't rise. Okay, physics, we don't do that. We sure need some equations to show our answer. So, before we start the question, I just want to be interested in whether you guys got a rise or fall. Okay, sorry, let me edit the poll. Yep, okay. Okay, so I've enabled a poll for y'all to interact with. Okay, if you can key in your answer, or if you didn't get the answer, just do a guess. Okay. %20 Wow, okay lor. So what was your answer 3 years ago? Is it the same as now? Forget already, right? Okay, most people say rise. Some people say fall. Okay. Oops. Nah, you can see. Most people, 30% of y'all say fall. 60% of y'all say rise. Okay, let's derive the answer together. Okay. Now, I'm going to show you all what happens. Oh yeah, sorry. So if I only gave you all those 2 options, means that it can't be no change. Okay. Don't do this question by intuition, because my intuition was also it will rise, but it turns out it will fall. Okay, let's prove that. Okay. Initially, right, I start with a cylindrical pond, and the water level is at a particular height. I don't care what it is. Okay, next, after I put the boat, okay, this is the boat, and this is the anchor, into my little cylindrical pond. Okay, the water level rises by or falls. I don't know. I can't. Okay. If I put those things in, definitely water level will rise, right? By a amount h. Okay. Now, let me denote the surface area, base area of the pond by capital H. Okay. Now, in the last case, I throw the anchor and the anchor sinks to the bottom. So I'm not very sure what will happen, but I know that the amount of water displaced, okay, will be given by H prime. So I define H prime as the new change in water height compared to the earlier case. So what we want to do is find the change in water height. Yeah, change in water height. Okay, and change is always final minus initial, right? Okay, there's two possibilities. Okay, or three. If this is positive, this is 0, and this is negative. Okay, if this quantity is positive, it means there's a rise. Oh shit. If this quantity is 0, there is no change. And if this quantity is negative, it's a fall. Okay, so let's check whether it's positive or negative. Okay, this part is going to be very, very technical. So I'm recording this lecture. If you miss it, right, you can reread it again. We have about 25 minutes. Let's do this. Okay. Sorry. H prime minus H. I said that already, Ying. Okay. Now, look at this case. Both of these objects are floating, right? If both of these objects are floating, we got the principle of flotation. Oh, what's this? U, total upthrust, equals to weight of the anchor plus weight of the boat. Okay, let's derive it. Okay, upthrust is actually equal to the weight of the fluid displaced. So it is H times the base area times the density of water times G. Okay. Faster go lor, then you just miss this small part lah. Okay. Weight of the anchor is given by volume of the anchor times density of the anchor times G plus volume of the boat times density of the boat times G. Okay. Now volume of the anchor is given by density of the sorry. Got the volume of the anchor already, so no problem. Okay. Now I want to make H the subject because I want to compare the H's. So H equals to VA rho A plus VB rho B over A rho water. Okay? So we got one result. Let's frame up this result nicely because we'll use it again later. Okay. Now, let's look at the second case. The boat is floating. But the anchor is not floating. Okay? If the anchor is not floating, but the boat is floating, we can't treat them in one equation like we did earlier, where upthrust is equal to weight of the anchor plus weight of the boat. Now we have to treat them separately. Okay, so let's treat them separately. Okay. And defining the new upthrust as U prime, it is equal to the upthrust that's acting on the anchor plus the upthrust that's acting on the boat. Okay, and these two are separate now. So the upthrust acting on the anchor no longer equal to the weight of the anchor because the anchor already sunk to the bottom. Okay, the upthrust is definitely not equal to the weight. That's only for floating objects. So since it's sunken, the only thing we know about the upthrust of the anchor is that's equal to the fluid that the anchor displaces. That means whatever volume that the anchor occupies in a fluid. So even though it's sunk to the bottom, it still has an upthrust, but it's just that it's not strong enough to overcome the weight anymore. So this upthrust is now equal to the volume of the fluid displaced, which is basically the volume of the anchor times the density of the fluid times G. And upthrust of the boat, okay, is equal to volume of the boat, density of the boat, times G. Let me repeat a little bit to clarify and for the benefit of Zixing. Okay. In the first case, the boat and the anchor are floating. Okay. So the upthrust that acts on this combined system is equal to the weight of both the boat and the anchor. So U equals to WA plus WB. This comes from our principle of flotation since both the anchor and the boat are floating. Alright. So we substitute the upthrust by the amount of fluid that is displaced by these two objects. We know that it's just H, which is the height of the water level that changes, times A, the base area of the entire body of water, times density of water, times G. So that's equal to the upthrust. Then the weight of the anchor and the weight of the boat is just density of the anchor, density of the boat, or the density of the boat times its volume times G. Okay, so we know those two stuff. And I make H the subject so that I got a very disgusting, complicated expression on the right hand side with lots of different unknowns. Because the initial case is that the boat and the anchor must be floating, if not they'll be sinking, right? Okay, to answer Anjali's question, I thought upthrust of the boat equals to volume of the boat times density of the water. No, that is true if the boat is inside the water, but the boat is not completely sunk inside. So I don't know what the volume of the boat that is inside the water is. But what I do know that is that the upthrust is equal to the two weights. Okay, basically it comes from what we did earlier on. Okay, if I have an object that is floating, the upthrust must be equal to the weight for it to remain floating. So that's how I know that the upthrust is equal to the volume or the weight of the boat plus the weight of the anchor. Does that make sense to you? Plus weight of the anchor. Yeah, height of the displaced water, not height of the entire water thing, because I didn't define it earlier. See, in the earlier example, I just left it like this. So I don't know what it is. H is just the change in the height of the water. Okay, from its original height. Okay, displaced water only. Correct. That's right. Well, very colorful are you? Okay. In the second case, right? Zixing, okay, listen up because you missed this. Okay, the anchor is thrown overboard. And the anchor has sunk to the bottom. It's not floating anymore. So our principle of flotation, which says that weight equal to upthrust, cannot hold anymore because it's no longer in equilibrium. It's sunk right to the bottom. Okay, but the boat, however, is still floating. So now the total upthrust that acts on both of these objects, okay, I can't treat them as one equation anymore. I have to treat them as two different equations. Basically, the total upthrust is the upthrust acting on the anchor and the boat separately. For the boat, right, it's easy because the boat is still floating. It is just the volume of the boat times density of the boat times G. Because the boat is still floating, okay, the principle of flotation still holds. But for the anchor, it's sunk right to the bottom. Okay, so since it's sunk to the bottom, right, I only know that the upthrust of the anchor is equal to the weight of the fluid displaced by the anchor. So it is VA times rho water times G. This is basically the amount of water that is displaced by the anchor. Okay? So now, we know UA and UB. Let's create an expression for U prime. Yeah, the height should increase, but we don't care because I never considered the amount of water that the boat displays. I only know that the boat is floating, so whatever it displays must be equal to the weight of the boat itself. It means why the density for anchor is not rho A. What's PAIDGIII? Okay. Basically, we have two principles, right? Okay, let me write it here. We have two principles. Okay, one is principle of flotation. So for an object floating in water, okay, upthrust is equals to weight. Okay. In the second case, we got the normal case of upthrust equals to volume of water times density of water times G. So these are two possible equations for upthrust. Agree? One is equal to weight if it's floating. This is only true for objects that float. And the other is upthrust equals to the volume of water displaced. Okay, this is always true. Always true. This one is special case. So for part B, okay, the anchor has sunk to the bottom. So I'm not using the special case. I'm just using the general equation that upthrust is equal to the volume of the fluid displaced. And since the anchor is completely submerged, the amount of water displaced is just the volume that the anchor occupies. So it's volume of the anchor times the density of the water times G. Okay, but for the boat, right, it's partially floating, so I don't know how much of it is submerged in the water. But I do know that it fulfills the special condition of flotation, so the upthrust is equal to its weight. And the weight of a boat is just the volume of the boat times the density of the boat times G. Okay, hope that answers your question. So we can maintain this equation. If you don't get it, you can watch the replay later when I upload it. Okay, U prime is the upthrust, the new upthrust. Okay, the new upthrust is nothing but, H prime times the base area times the density of water times G. Okay, and the right hand side is whatever is above there. So I make H prime the subject. I get VA rho W plus VB rho B over A rho W. So I have a result for H prime as well. Okay. Now I'm going to transfer both of these to a new sheet. Okay. H is H prime minus half H. So it is equal to VA rho W plus VB rho B minus away the result for H, which is here, VA rho A plus VB rho B. Okay, the denominator is some random nonsense that I don't care about. It's a positive number. Yeah, if you need to go, just go first. Okay, so what happens is that, look at the numerator. I'm left with VA rho W minus VA rho A. The other two terms cancel themselves out. Okay, and the denominator is some positive number that I don't care what it is. Okay, now this numerator, right, take a look at it. The volume of the anchor times density of the water minus the volume of the anchor times density of the anchor. Is it a positive or negative number? It's totally negative, right? Because the density of water is less than density of anchor. So, if this numerator is negative, it means that, Anjali, how do I know that it's negative? Density of water greater or density of anchor greater? I mean, assuming an anchor is made of metal and water is made of water. Right? So density of water must definitely be less than density of the anchor. So the numerator must be negative. No need to assume that density of water is definitely less than the density of an anchor. Right? What's anchor made of? Yeah, metal density is definitely greater, right? Exactly. Okay. So if density of water is less than the density of the anchor, it just means that h prime minus h is going to be negative. If it is negative, then the height of the water will fall. Okay? And the difference comes because when an anchor is floating on top of a wood, okay, the upthrust is equal to the weight of both of these objects. But the moment the anchor is sunk right to the bottom, okay, the upthrust is not equal to the weight of both of the objects. Okay? Why? Because let me draw you a diagram for the anchor once it has sunk. When the anchor has sunk to the bottom, okay, that what are the forces acting on it? When it has sunk to the bottom, oops, there is an upthrust. Okay. There is also the weight of the anchor. But since it's lying on the bottom of the ocean bed, there is an additional normal force. So in the previous example, when it was floating on top of the boat, right, UA was equal to WA. But now UA, when it has sunk to the bottom, okay, is equals to WA plus the normal reaction force. Also to say, UA after it has sunk to the bottom, okay, is less than the original upthrust when the anchor is actually floating on top of the boat. This UA is for when the anchor is floating on top of the boat, okay, in this case here. Anybody got any violent objections or don't understand this explanation? Okay, I recorded this, so try to replay this part, okay, because I don't have much time left. This thing cuts off itself as I learned from the previous lesson. Yeah, it will displace pond water, but less than the total effect of the anchor and the boat when it was floating. Because look at the equations. See, initially the upthrust was due to the weight of the anchor and the weight of the boat. But once the anchor has sunk, the total upthrust is no longer equal to the combined weight. It's equal to less than the combined weight. So the total upthrust in the first part is slightly more, okay, I don't know much more, slightly more than the second part by this numerator term here. Okay, by this numerator term. Oops. By this numerator term. Now, upthrust is the only thing that affects the height of the water. The height of the water meaning the height of the water increased from its original height. Because upthrust, right, is equal to the whatever the fluid that is displaced. So when the fluid is displaced, it just makes the level of the pond higher. It can't make the level of the pond low. It can't affect anything else but the height of the pond, right? Because whenever the water is displaced, it will just cause the pond height to increase. See, from the original case. So the pond's volume never changes, okay, but the height will change depending on the upthrust, right? So what it means to say is, yeah, if you need to go ahead. Okay, no worries. What I mean to say is the pond level will be higher, okay, depending on the upthrust that the total system experiences, the anchor and the boat together. So if the upthrust in the case where they are floating is higher, then the level of the pond will be higher. If the upthrust after the anchor is thrown into the water is higher, then the water level will rise. Okay, but unfortunately in this case we have shown that the numerator here is a negative numerator. So if it's a negative numerator, it means that the upthrust when after the anchor was thrown in, the total upthrust of the anchor and the boat is lesser than before when the anchor was floating on top of the boat. So therefore, the height of the water must decrease. What do you mean if the anchor wasn't originally in the boat? That means you stand at the bank and then you throw in the anchor into the pond. Yes, then the total level would rise even further because the anchor wasn't in the system in the first place. But now we are comparing the system where the anchor was already in the system. See, the anchor was just on top of the boat. So now what happens is I throw the anchor overboard, that's all. But if someone on the river bank, okay, stands and throws the anchor in, of course then the water level will rise. It will rise by exactly the amount that you think it would rise by. Okay? Yeah, you can say the denominator is a positive number, that's correct. Okay, let me answer the questions that is posed. Okay, a few came up together. Okay. To answer Ik Ming, big A is the area of the pond, the surface area of the pond, the base area of the pond. That is here. Okay, big A is the base area of the pond. Sorry. Small a is the anchor. Okay. Yeah, the explanation is actually within all of these equations here so far. Okay, so if you have written down all these equations, okay, and say that delta H negative means it will fall, prove that delta H is negative, you have proven that the water level will fall. So this is what I mean by proving it. And this explanation totally proves it in a very rigorous manner. Okay, if you're able to write this down, you'll get the answer. Okay, otherwise you have to rely on some qualitative explanation like what I tried to explain. Oh, the upthrust is actually lesser in this case. It's not say it won't be accepted, but when I have the equations, it becomes very quantitatively clear. Okay, that I have this expression here is negative, so therefore the water level must fall. Okay, if you have any more questions, right, you can ask me when we are back at school again, because this live class will end in a minute or so. Okay, I'll save the video. If you still have any problem understanding it, do go and review it. Okay, Zixing and Ik Ming. Okay, if you have any problem, you can go ahead and review it. But other than that, no problem. Let me do the uploading after this. Okay, let me end the debut now.